Imagine a sleek, autonomous vehicle cruising down a dark, rain-slicked highway. Without warning, it slams on the brakes. The culprit? A flat, harmless drain cover embedded in the asphalt. An investigator would find that the brake pads didn't lock up, and the software didn't crash. Every physical component on the vehicle executed its job with absolute precision. For decades, automotive safety focused on physical durability. Traditional standards like ISO 26262 were designed to ensure that wires don't short-circuit and sensors don't arbitrarily snap. But that focus on hardware leaves a gap in modern robotics. Machines are now hitting the road with perfectly intact hardware, yet their internal model of the world is wrong, interpreting a flat drain cover as a solid wall. To address this, the industry developed a standard called SOTIF, the Safety of the Intended Functionality. It provides a framework to prevent accidents that occur when a mechanically sound system acts on a flawed perception of its environment. SOTIF moves past the domino effect model of safety. In complex systems, a crash rarely stems from one broken part knocking over the next in a simple linear chain. Instead, an autonomous vehicle functions like a symphony orchestra. If the brass and the strings are out of sync, the result is dangerous dissonance, even if every individual musician plays their notes correctly. To manage this synchronization, developers use a methodology called STPA, or System-Theoretic Process Analysis. This approach treats safety as a pure matter of control. Strengthening a steel bumper does nothing to stop a logic error. The focus must be on how the system manages its own behavior. This architecture relies on a continuous loop. Sensors perceive the environment, the processor makes a judgment, and the actuators execute a physical movement. Modern engineering focuses on the space between these nodes. Safety is found in the reliability of the interactions and the feedback loops, not just the strength of the individual components. In STPA, engineers first define an overarching safety goal, like maintaining minimum safe distances. Step 2 maps authority layers, from route planning down to operational steering commands. Step 3 identifies unsafe control actions, where a healthy processor issues a dangerous command, like acting too late. The final step traces these actions back to their source, pinpointing the specific environmental conditions that trigger the mistake. Consider a vehicle on a fog-covered highway. The camera sensors encounter a sudden drop in contrast and struggle to classify a shadowy shape in the lane ahead. Dealing with low-confidence data, the processor hesitates. It waits for more frames of video to clear up the image, consuming precious milliseconds. When the system finally confirms the obstacle and slams on the brakes, the stopping distance is already gone. The car crashes because a correct command arrived a fraction of a second too late. A failure of timing rather than a failure of hardware. No human test driver can cover enough miles to experience every possible variation of fog, shadow, or road debris. Industry leaders overcome this by using cloud-based virtual environments. These platforms simulate millions of miles of edge case scenarios to see exactly where the logic might fail. The insights from this analysis are turned into mathematical safety constraints. These are a separate set of rules that monitor the autonomous driver in real time. This creates an active guardrail. If the AI attempts a maneuver that is mechanically sound but situationally dangerous, this secondary system immediately intervenes to prevent an accident. The massive computing power required to map these risks results in a vehicle that moves through the world with quiet, seamless confidence. We have reached a point where building an unbreakable car is merely the first step. A perfectly manufactured chassis cannot guarantee a safe autonomous decision. The focus of engineering has expanded from the durability of the machine to the wisdom of its actions, ensuring that even in an unpredictable world, the machine remains in total control.